While examining the starting points of the universe, many inquiries strike a chord. What went before the enormous detonation? Assuming that there was no before, what caused the huge explosion? Hundreds of years prior, the response appeared to be direct. A heavenly being got everything rolling. Even Isaac Newton accepted that God made the universe about 6,000 years back. Later researchers, including a youthful Albert Einstein, expected the universe to be everlasting and perpetual. Stars could form and die, planets could impact, and movements could rise and fall, yet on a grand scale the universe seemed consistent. It was only after the 1930s that persuading proof for the universe's expansion arose, and by the 1960s, the possibility of the Big Bang as the universe's starting point became widely accepted. This upheaval in how we understand the universe was as significant as the shift to a heliocentric model of the solar system. However, this new viewpoint raised additional questions. What was before the Big Bang? What was the nature of space before it started to expand? And if everything starts, should it end? Prestigious physicist Brian Cox has delved into these profound questions, offering a pivotal perspective. Cox suggests that the universe existed before the Big Bang, challenging conventional notions of our cosmic beginnings. He explains that while the universe likely began in a very hot and dense state known as the Big Bang, this was not necessarily the start. According to Cox, it's possible to talk about a time before the Big Bang. His work has made complex scientific ideas more accessible to the public. His investigation of the theory of cosmic inflation takes us back to the mid-20th century, when observations of distant galaxies showed they were receding from us, a discovery that aligned with Einstein's general relativity. This recession indicated a growing universe, implying that in the distant past, everything was closer together. A growing universe also means that as time progresses, light stretches, cooling the universe. By extrapolating backward, scientists arrived at a state where the universe was so hot that atoms couldn't form. This led to the prediction of the cosmic microwave background, CMB, an afterglow of the Big Bang found in 1964 by Arno Penzias and Robert Wilson. This discovery confirmed the Big Bang theory, suggesting the universe began from an incredibly hot and dense state. But how far back can we extrapolate? Can we reach a state where matter and antimatter pairs form suddenly, or where even protons and neutrons degrade into a quark-gluon plasma? These considerations lead to an alternative view of the universe's origin. Rather than a specific hot, dense state, the early universe might have undergone a period of astronomical inflation, where space itself expanded rapidly. This period set the stage for the Big Bang but didn't create a singularity. What happened before inflation, or whether inflation was timeless, remains an open question. It is clear, though, that the Big Bang was not a definitive beginning. So if not the Big Bang, what was the origin? The short answer is that we don't know for certain, but there are intriguing possibilities. One idea is that before the Big Bang, the universe was an infinite stretch of ultra-hot dense material governed by quantum mechanics. The Big Bang could mark the transition to a universe driven by classical physics. Stephen Hawking's no-boundary proposal suggests that before the Big Bang, reality was finite but without boundaries, similar to the surface of the Earth. On the other hand, Brian Cox proposes a scenario where the universe didn't exist before the Big Bang. Rather, there was a vast expanse of energy in a state of near quietude, gently oscillating. This energy caused rapid expansion known as inflation, eventually converting into matter and leading to the universe we know. Cox's ideas challenge traditional creation stories, suggesting that inflation imprinted patterns into our universe, forming regions of varying densities. These dense regions eventually collapsed to form the first stars and galaxies, ultimately leading to the formation of our solar system. Remarkably, Cox is not alone in these views. Theoretical physics suggests that the universe may be part of a cycle of big bangs and big crunches, extending back and forth in time. This idea, rooted in string theory, posits that the universe undergoes cycles of expansion and contraction. While early versions of this model struggled to match observations, recent developments have refined the theory, suggesting that a cyclic universe may be possible. The cyclic model challenges traditional views, proposing that the universe's expansion and contraction are part of a larger eternal process. This model also offers an alternative to the inflationary model, which posits an infinite number of universes within a multiverse. Instead, the cyclic universe suggests a more comprehensive explanation without requiring multiple universes. A variation of this hypothesis is the Big Bounce, where the universe expands and contracts in cycles. Some versions propose this happens once, while others suggest it occurs endlessly. The Big Bounce model still requires significant theoretical leaps but challenges the idea of a singular beginning. Critics of the inflationary theory argue that it is too complex and contrived, suggesting that an alternative like the Big Bounce could provide a simpler, more comprehensive explanation. The cyclic universe proposes that time might run backward in a mirror universe, potentially explaining dark matter and other cosmic phenomena without requiring a complete understanding of the universe's origin. The quest for a complete theory of everything continues, with imaginative ideas testing conventional cosmology and offering new insights into the universe's true nature. Join us as we explore how Brian Cox has challenged the theory of cosmic inflation and made science accessible to the public, contributing to discussions on these profound questions. The idea of the Big Bang first emerged in the 1920s and 1930s when astronomers observed that distant galaxies seemed to be receding from us. According to Einstein's general relativity, a static universe would be gravitationally unstable. Everything would have to either be moving apart or collapsing together. Observations of this apparent recession showed that the universe was expanding. An expanding universe means that things were closer together in the distant past. This also implies that light in the universe stretches in wavelength over time, cooling the universe as it ages. Extrapolating this far enough back, we reach a state where everything was hot enough that neutral atoms couldn't form. If this were accurate, we should see an additional glow of radiation today, which was indeed found in 1964 as the cosmic microwave background, CMB. This discovery confirmed the theory of cosmic inflation. However, extending this backward to a singularly hot dense state suggests a singularity, a point of infinite density that our current physics can't adequately describe. Instead, Cox proposes that the early universe was not simply a singularity but rather a complex state that evolved through processes that are not yet fully understood. His perspective challenges the notion of the Big Bang as a definitive beginning and suggests that what we see as the beginning could be part of a more extensive ongoing cycle. Cox's views align with some aspects of the cyclic model, where the universe undergoes repeated phases of expansion and contraction. This model, though still speculative, offers a framework where the Big Bang could be just one event in a series of cosmic cycles. The idea of a cyclic universe suggests that each Big Bang might be followed by a big crunch, leading to a new cycle of expansion. This contrasts with the traditional Big Bang theory, which posits a singular origin point for the universe. In exploring these concepts, Cox and other physicists delve into questions about the nature of time, space, and the fundamental forces of the universe. For example, the concept of cosmic inflation, a rapid expansion that occurred immediately after the Big Bang, has been crucial in explaining the uniformity of the universe and the distribution of galaxies. However, the ultimate nature of this inflationary period and its implications for the universe's future remain subjects of intense research. Furthermore, theories such as string theory and quantum gravity offer additional insights into the conditions that might have preceded the Big Bang. These theories attempt to reconcile quantum mechanics with general relativity and provide a more comprehensive understanding of the universe's origins and its ultimate fate. String theory, for instance, suggests that the fundamental building blocks of the universe are not point-like particles but rather one-dimensional strings that vibrate at different frequencies. In summary, while the Big Bang theory has significantly advanced our understanding of the universe's origins, it is not the final word. The questions about what came before the Big Bang, the nature of cosmic inflation, and the possibility of a cyclic universe continue to drive scientific inquiry. The exploration of these questions pushes the boundaries of our knowledge and challenges our understanding of the cosmos. As research progresses, new observations and theoretical advancements will continue to shape our understanding of the universe's history and its ultimate destiny. The search for a complete theory of everything remains one of the most profound and exciting endeavors in modern science, promising to reveal new and transformative insights into the nature of reality. The quest to understand the origins of the universe has captivated human imagination for centuries, evolving from mythological narratives to rigorous scientific inquiry. While the Big Bang theory revolutionized our understanding in the 20th century, It left fundamental questions unanswered and raised new ones about what came before and what lies ahead for the cosmos. One of the most intriguing aspects of cosmology is the concept of time itself. The Big Bang suggests a beginning, a moment when space and time as we know them emerged from a state of infinite density. However, this view is challenged by theories that propose a cyclical nature of the universe, where expansion and contraction occur in a recurring pattern. This cyclic model suggests that time may not be linear but instead part of a larger cosmic rhythm, where each cycle of expansion ends in a contraction, potentially leading to a new cycle of creation. In recent decades, advances in theoretical physics have provided new frameworks to explore these ideas. String theory, for instance, proposes that the universe consists of tiny, vibrating strings of energy. These strings vibrate at different frequencies, giving rise to the particles and forces that govern our universe. String theory also suggests the existence of multiple dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension, offering a potential explanation for the origins of space and time themselves. Within string theory, the concept of branes, short for membranes, provides another avenue for understanding cosmic origins. Branes are higher-dimensional objects that can collide and interact in ways that influence the evolution of the universe. In some versions of string theory, our universe is envisioned as a brane embedded in a higher-dimensional space, with interactions between branes giving rise to phenomena such as inflationary bursts of expansion. The concept of inflation, proposed in the 1980s, remains a cornerstone of modern cosmology. Inflation suggests that in the earliest moments of the universe, a rapid and exponential expansion occurred, stretching the fabric of spacetime from subatomic scales to vast cosmic dimensions. This period of inflation would explain the uniformity of the cosmic microwave background radiation observed today, as well as the distribution of galaxies across the universe. While inflation provides a compelling explanation for certain observed phenomena, its precise mechanism and origin remain subjects of ongoing research and debate. Some physicists have proposed variations of inflation, such as eternal inflation, which suggests that inflationary processes continue indefinitely, leading to the creation of multiple pocket universes within a larger multiverse. Each pocket universe may have different physical constants and laws of physics, potentially explaining the fine-tuning of our own universe for life. The idea of a multiverse, where our universe is just one of many possible universes with different properties, challenges traditional notions of cosmic uniqueness and raises philosophical questions about the nature of reality and our place within it. If the multiverse exists, it could mean that the conditions for life, as we know them, are not unique to our universe but rather the result of a cosmic lottery where different universes have different outcomes. Beyond theoretical speculation, observational cosmology continues to provide new insights into the universe's history and structure. The discovery of dark energy in the late 1990s revolutionized our understanding of cosmic expansion, suggesting that the universe's expansion is accelerating rather than slowing down as previously thought. Dark energy remains one of the greatest mysteries in physics, comprising roughly 70% of the energy density of the universe yet remaining undetected directly. Similarly, dark matter, a form of matter that interacts gravitationally but not electromagnetically, accounts for approximately 27% of the universe's energy density. Its existence is inferred from gravitational effects on galaxies and galaxy clusters, yet its precise nature remains unknown. Understanding dark matter is crucial not only for deciphering the universe's structure on large scales, but also for testing the validity of fundamental physical theories. The interplay between dark matter, dark energy, and ordinary matter, comprising less than 5% of the universe's energy density, shapes the cosmic web of galaxies and galaxy clusters observed through telescopes. These structures provide clues about the universe's evolution from its earliest moments to the present day, offering a cosmic fossil record that astronomers and cosmologists decode to understand the processes governing its growth and development. In recent years, technological advancements in observational astronomy have led to unprecedented discoveries, such as gravitational waves, ripples in spacetime caused by cataclysmic events such as the collision of black holes. The detection of gravitational waves in 2015 confirmed a prediction made by Albert Einstein's general theory of relativity a century earlier, opening a new window into the study of the universe's most extreme phenomena. Gravitational wave astronomy promises to reveal insights into the nature of black holes, neutron stars, and other exotic objects that defy conventional understanding. By observing these cosmic collisions, scientists can test theories of gravity in extreme conditions and probe the fundamental properties of spacetime itself. Meanwhile, experiments at particle accelerators such as the Large Hadron Collider (LHC) seek to recreate conditions similar to those just after the Big Bang. By smashing protons together at nearly the speed of light, physicists aim to unlock the secrets of the early universe and explore the fundamental forces and particles that govern its behavior. These experiments provide empirical data that complement theoretical models, offering insights into the universe's fundamental building blocks and their interactions. One of the enduring mysteries of cosmology is the ultimate fate of the universe. Depending on its density and the nature of dark energy, the universe may continue expanding indefinitely, eventually becoming cold and dark, a scenario known as the heat death or big freeze. Alternatively, if dark energy behaves differently or if the universe contains enough matter to reverse its expansion, a big crunch could occur, collapsing the universe back into a hot, dense state similar to the Big Bang. The possibility of a cyclic universe, where these phases of expansion and contraction repeat indefinitely, offers another perspective on cosmic destiny. In such a scenario, each cycle may lead to the formation of new galaxies, stars, and potentially life, perpetuating a cosmic drama on scales of time and space beyond human comprehension. As our understanding of the universe evolves, so too does our appreciation of its profound mysteries and beauty. From the smallest subatomic particles to the largest cosmic structures, the universe continues to challenge our imaginations and expand our knowledge. The search for a complete theory of everything, a unified framework that reconciles quantum mechanics and general relativity, remains a central goal of modern physics, promising to reveal the underlying principles that govern the cosmos and our existence within it. In conclusion, the exploration of the universe's origins and ultimate fate represents one of humanity's greatest intellectual endeavors. Through theoretical speculation, observational discovery, and experimental verification, scientists seek to unravel the cosmic tapestry that has unfolded over billions of years. Each new observation and theoretical breakthrough brings us closer to understanding the nature of reality itself, pushing the boundaries of human knowledge and inspiring generations to come.